Hi friends, welcome to the lecture of linear algebra. In last lecture we have completed what is a dual space. Dual space is simply nothing but it is a collection of linear functionals on a vector space V2 filled F, that is V over F to F over F. Now today we have to see what is a basis for that dual space, that is a dual basis. We have to see what is a dual basis. Now let alpha 1, alpha 2, up to so on, alpha n be a basis for a vector space V over a field F over a field F. Now let F1, F2 up to so on Fn belonging to V star, as these are the members of V star and V star is nothing but the collection of linear functions. Then F1, F2 up to so on Fn belongs to V star are the linear functionals, linear functionals defined by f of phi of alpha j is equal to delta ij equal to 1 whenever I is equal to j and equal to 0 I is not equal to j, or delta ij will be equal to 1 whenever I equal to j and is equal to 0 whenever otherwise. Now this fi of alpha j will be equal to delta ij is also called a Kronecker delta. This delta is also called as a Kronecker delta. Okay. So we have defined these linear functions as a fi of alpha j will be equal to 1 whenever I is equal to j and equal to 0 whenever I is not equal to j. Then the set of n functionals f1, f2 up to so on fn forms a basis for vector space V star, that is the dual space or V star, and this basis is called, and this basis f1 up to so on fn is called a dual basis. Called a dual basis. What is a dual space? Dual space is simply nothing but it is a collection of linear functionals, and we have to find out the basis for that dual space, and which is a dual basis. So dual basis is nothing but if we have given and basis for a vector space V over F, that is the basis elements are alpha 1, alpha 2 up to so on alpha n, then the collection of n linear functionals F1, F2 up to Fn belonging to V star is a collection of linear functions defined by phi of alpha j will be equal to delta ij, which is equal to 1 whenever I will be equal to j and equal to 0 whenever I is not equal to j. Then the collection of these n linear functionals f1, f2 up to so on fn forms a basis for dual space V star, that is a vector space V star. Then this new basis which contains n elements f1, f2 up to so on fn is called a dual spaces for a vector space V star. And we can also say that we say that functional fi is dual of basis elements alpha j whenever I and j running from 1 to n. So this is the dual basis. Let us see by taking some examples how will you find out the dual basis from a given basis of a vector space V over F. R to be a vector space over a field R over a field R if B equal to, that is basis set B equal to 1 0 comma 0 1 be a basis for R2 over R, then find two dual basis. So here R to be a vector space over a field R and basis set of R2 over R is given, that is 1 0 and 0 1, which is the standard basis of R2. Be a basis for R2 over R, then find its dual basis from given that B equal to 1 0 comma 0 1 be a basis of R2 over R. Then by definition of dual basis, let us take alpha 1 as 1 0 and alpha 2 is equal to 0 1. So B equal to alpha 1 comma alpha 2 is the basis for a vector space V, that is R2 over R. Now from definition of dual basis, let B star equal to F1 comma F2 be a dual basis. Okay, as F1 comma F2 be a dual basis, now we have to find out the value of these F1 and F2. Now by definition of dual basis, by definition of dual basis, this is Fi of alpha j equal to delta ij is nothing but 1 whenever I is equal to j and equal to 0 whenever I is not equal to j. So here we have two elements in basis of a vector space R2 over R. Then F1 of alpha 1 as I is equal to j, F1 of alpha 1 will be equal to 1, F1 of alpha 2 is equal to 0 since 1 is not equal to 2. Similarly, F2 of alpha 1 is equal to 0 and F2 of alpha 2 is equal to 1. So this is from given definition of a dual basis. Now let xy belonging to x comma y belonging to R2 be any element of R2 or R or be any vector. Okay. Now as F1 and F2 are two linear functionals, that is linear functionals are nothing but it is a mapping from vector space V over F to F over F, that is F over F, it means dimension of this F over F is 1. Then this linear functional gives some scalar value. Then for F1 of xi x comma y is nothing but some ax plus by by linear combination. As F1 is a linear functional, then F1 of xy can be written as a linear combination of these elements since F1 is a linear functional. So which is equal to h plus by be a scalar value which is belonging to codomain. Now and F2 of xy will be equal to some cx plus dy. Now as F1 of alpha 1 will be equal to 1, as F1 of alpha 1 is equal to 1, which implies what is the value of alpha 1? F1 of 1 0 is equal to 1, which implies from this definition F1 of 1 comma 0 will be equal to 1. Put x equal to 1 and y equal to 0, then we get A into 1 plus B into 0 is equal to 1, which implies A equal to 1. Now, similarly, F2 of F1 of alpha 2 equal to 0, which implies F1 of 0 1 is equal to 0. That is A into 0 plus B into 1 equal to 0, which implies B equal to 0. Again, similarly, F2 of alpha 1 is equal to 0, which implies F2. F2 is nothing but put alpha 1 as a F2 of alpha 1 comma 0 equal to 0, which implies C into 1 plus D into 0 will be equal to 0. That is C equal to 0. And now F2 of alpha 2 equal to 1, which implies F2 of 0 1 is equal to 1. That is C into 0 plus D into 1 equal to 1, which implies D equal to 1. So here we get the four values of A, B, C and D. A equal to 1, B equal to 0, C equal to 0 and D equal to 1. Put these values in. F1 of xy equal to x plus by and F2 of xy will be equal to cx plus dy. Then we get F1 of xy equal to A equal to 1 and B equal to 0, which implies F1 of xy equal to x, and F2 of xy equal to C equal to 0, D equal to 1, which implies what? Which implies set F1 and F2 is nothing but x comma y, and which is the dual basis for a vector space V over F. That is, if we have given one basis set B equal to 1 0 comma 0 1, then its dual basis is set which contains elements x and y. That is which is equal to some V star, which is the dual basis for a vector space V star. Okay. There is one another method to find out the dual basis. That is OR definition, OR method. Suppose as we have f1 of alpha 1 will be equal to 1, f1 of alpha 2 will be equal to 0, f2 of alpha 1 will be equal to 0 and f2 of alpha 2 will be equal to 1. Now, OR method is if xy belonging to R2 be any vector as xy belonging to R2 and the basis set of R2 is given, that is 1 0 and 0 1, then this xy can be written as a linear combination of that two basis set elements which are alpha 1 and alpha 2. Then x and y can be written as A alpha 1 plus B alpha 2. Since alpha 1 and alpha 2 are two basis elements of a vector space R2 over R, as this is now. From that, if we take a linear functionals on both sides, that is f1 and f2, then we get f1 of xi y will be equal to, as f1 and f2 are two linear functions, which implies here into f1 of alpha 1 plus b into f1 of alpha 2, and which is equal to f1 of alpha 1. As I equal to j by connected delta, f1 of alpha 1 will be equal to 1, which is a into 1 plus b into, as 1 is not equal to 2, its value is 0, which is equal to a, and f2 of xy will be equal to a into f1 of a into f2 of alpha 1 plus b into f2 of alpha 2, which is equal to a into 1 into 2 is not equal to 1, which implies 0 plus b into 1, which is equal to b. So here we get f1 equal to a and f2 equal to b, and these a and b are any two arbitrary constants. Now we have to find out the values of these a and b. As x and y can be written as linear combination of these elements, then Put the value of alpha 1 and alpha 2. Then x comma y will be equal to a into alpha 1 is 1 comma 0 plus b into 0 comma 1, and which is nothing but a 0 plus 0 1, and which is equal to a sorry b comma b. As these two ordered pairs are equal, and we know that two ordered pairs are equal if and only if the corresponding elements will be equal. X equal to a and y equal to b. Now put these values in these linear functions, so we get f1 will be equal to x and f2 will be equal to y, and these are the, and they said x comma y forms a dual basis of a dual space. Okay. This one is the another method to find out the dual basis. Now second example. Let b equal to minus 1 1 1 1 minus 1 1 1 1 minus 1 is a basis for a vector space V3 over R, then find dual basis. Okay. Here we have given one basis set, which is the basis for a vector space V over here, V3 over R. Now we have to find its dual basis. Given that V equal to minus 1 1 1 1 minus 1 1 and 1 1 minus 1. Now, by definition of dual basis, take this one first element as alpha 1, second one as alpha 2, and the third one as alpha 3, which implies if this one will be equal to alpha 1, equal to alpha 2, and equal to alpha 3. Here, basis of V over R. Now, which implies V equal to say alpha 1, alpha 2 and alpha 3 is a basis for V3 over R. Now, by definition, let V star will be equal to F1, F2, F3 be a dual basis, which is from definition of a dual basis. Now, from definition, f1 of alpha 1 is equal to 1, since I will be equal to j. f1 of alpha 2 equal to 0. Similarly, f1 of alpha 3 is again 0. f2 of alpha 1 is 0, as I is not equal to j. f2 of alpha 2 equal to 1. f2 of alpha 3 is again 0. Similarly, f3 of alpha 1 equal to 0, f3 of alpha 2 is equal to 0, as I is not equal to j, and f3 of alpha 3 is 1, since I is equal to j. Now, let x, y, z belonging to V3 over I be any vector. X, Y, Z belonging to V3 over R be any vector. Which implies now we can use any of these two methods to find out the dual basis. So let f1 of xyz, f1 of xyz And we know that F1, F2, F3 are three linear functions since they are belonging to V star. As they are linear functional, then they hold the linearity property. Then this these element x, y, z can be written as a linear combination, which is equal to some a1 x plus a2y plus a3z has linearity property. That is, we can write it as a linear combination. F2 of x, y, z is equal to some b1x plus b2y plus b3z. Now, and f3 of xyz is equal to c1x plus c2y plus c3z. Now, first find for f1. Now, here these are the this is from dual definition of dual basis. Now, as we have f1 of alpha 1 is equal to 1, f1 of alpha 1 will be equal to 1, and alpha 1 is nothing but minus 1 1 1, which is equal to 1, which implies put these values minus 1 1 as a in first one, we get minus of a1 plus a2 plus a3 is equal to 0. Sorry, is equal to 1. This one is the first one. And f1 of alpha 2 is equal to 0, which implies f1 of 1 minus 1 1 equal to 0, which implies a1 minus a2 plus a3 is equal to 0. And this one is the second one. And third one is f1 of alpha 3 equal to 0 implies f1 of 1 1 minus 1 equal to 0. That is a1 plus a2 minus a3 is equal to 0. Now, from this 1, 2, 3, we have to find out the values of A1, A2 and A3. And if we find out the values of A1, A2, A3 and put it in this one, then we get the first basis element F1. Now, from 1 and 3, minus of A1 plus A2 plus A3 equal to 1, and A1 plus A2 A1 plus A2 minus A3 equal to 0. This is from equation 1 and 3. Now add these two. We get by taking addition. We get minus A1 plus A1 0 and plus A3 minus A3 0, and A2 plus A2 2A2. 2A2 will be equal to 1 plus 0 1, which implies A2 is equal to 1 by 2. Now from 2 and 3, A1 minus A2 plus A3 equal to 0, A1 plus A2 minus A3 equal to 0. Now again add these two, minus A2 plus A2 0 plus A3 minus A3 0, and 2A1 is equal to 0, which implies A1 equal to 0. A1 equal to 0, A2 equal to 1 by 2. Put these values in equation. Put this in equation 2. Then we get A1 will be equal to put A1 and A2 in 2. We get A1 is 0 minus A2 is 1 by 2 plus A3 is equal to 0, which implies A3 is also 1 by 2. So here we get A1, A2, A3. Now, so A1 is equal to 0, E2 equal to 1 by 2 and E3 is equal to 1 by 2. Now we have to find out the values of B1, B2 and B3 and C1, C2 and C3. Now F2 of alpha 1 will be equal to F2 of alpha 1 equal to 0, which implies F2 of alpha 1. And here alpha 1 is nothing but minus 1, 1, 1. F2 of minus 1, 1, 1 equal to 0, and which is minus of A1 plus, sorry, F2 is minus of B1 plus B2 plus B3 is equal to 0. This one is sum 4. F2 of alpha 2. Alpha 2 is 1 minus 1, 1. Equal to F2 of alpha 2 is 1, which implies B1 minus B2 plus B3 is equal to 1. This is the fifth one. And F2 of alpha 3. Alpha 3 is 1, 1 minus 1 equal to 0. B1 plus B2 minus B3 is equal to 0. This is the sixth one. Now we have to find out the values of B1, B2 and B3 by taking 4th and 6th from 4th and 6th. We get minus of B1 plus B2 plus B3 equal to 0, and B1 minus B2 plus B3 is equal to 0. And now adding these two, B1 B1 cancel and B3 B3 cancel. Sorry, B2 B2 cancel. Then we get 2 B3. Sorry. B1 plus B2 minus B3 from 4 and B1 plus B2 minus B3. B1 B1 cancel and B3 B3 cancel. 2 B2 will be equal to 0. From this, B2 equal to 0. Now, from 5 and 6, B1 minus B2 plus B3 equal to 1. B1 plus B2 minus B3 equal to 0. Now, adding again these two, we get B2 B2 cancel, B3 B3 again cancel. 2B1 is equal to 1, which implies B1 will be equal to 1 by 2. Now, put B1 equal to 1 by 2 and B2 equal to 0 in 6. B1 equal to put B1 and B2 in 6. We get B1 is 1 by 2 plus B2 is 0 minus B3 is equal to 0, which implies B3 is 1 by 2. So B3 will be equal to 1 by 2. Now, from this, we get again three values B1, B2, B3. So, B1 equal to 1 by 2, B2 equal to 0, and B3 is equal to 1 by 2. Now it remains to prove that now it remains to find out the values of C1, C2 and C3. Now, F3 of alpha 1 equal to F3 of alpha 1 is minus 1, 1, 1 equal to F3 of alpha 1, F3 of alpha 1 equal to 0, which implies F3 is minus of C1 plus C2 plus C3 is equal to 0. This one is the seventh one. Now, F3 of alpha 2, 1 minus 1, 1 equal to 0, which implies C1 minus C2 plus C3 equal to 0. This one is the equation A. And F3 of alpha 3 is 1, 1 minus 1, and which is equal to 1, which implies C1 plus C2 minus C3 is equal to 1. Now, from 7 and 9, 7 and 9, that is adding 7 and 9, we get minus of C1 plus C2 plus C3 is equal to 0. C1 plus C2 minus C3 equal to 0. Now adding these two, we get 2C2, sorry, C1 plus C2 minus C3 will be equal to 1. 2C2 is equal to 1, which implies C2 equal to 1 by 2. And from 8 and 9, C1 minus C2 plus C3 equal to 0. C1 plus C2 minus C3 equal to 1. So from this to 2C1 will be equal to 1, which implies C1 equal to 1 by 2. Put C1 and C2 in 8. Put C1 and C2 in 8. We get C1 is 1 by 2 minus C2 is again 1 by 2 plus C3 is equal to 0. 1 by 2, 1 by 2 cancel, which implies C3 is equal to 0. So we get three values C1, C2 and C3. And C1 equal to 1 by 2, C2 equal to 1 by 2, and C3 is equal to 0. Now we have to put these values of A1, A2, A3, B1, B2, B3, C1, C2, C3 in these equations. Then we get three linearly independent elements of a basis set. So from this, F1 is nothing but by putting all these, we get F1 of XYZ is equal to A1 equal to 0, A2 equal to 1 by 2, A3 equal to 1 by 2. A1 equal to 0, then A2 is 1 by 2 plus A3 is 1 by 2, which is implies 1 by 2 into Y plus Z. That is 1 by 2Y plus 1 by 2Z is equal to 1 by 2 Y plus Z. Similarly, F2 of XYZ is equal to 1 by 2. Here, B2 is 0. Then it is 1 by 2x plus 1 by 2z, which is equal to 1 by 2x plus z. And F3 of XYZ is equal to 1 by 2x plus 1 by 2 y, which is nothing but 1 by 2 x plus y. So we get the basis set F1 is nothing but 1 by 2 y plus z, 1 by 2 x plus z, comma 1 by 2 x plus y is a dual basis. So this one is the dual basis for a given vector space. Okay. Now third one example is let B equal to T1 comma T1 here basis of R2 over R. Then find the dual basis. Now b equal to, let alpha 1 is nothing but 2 comma 1 and alpha 2 is equal to 3 comma 1. Now again let b star is equal to f1 comma f2 be a dual basis. Okay, and this one is the dual basis. Then by definition of dual basis, f1 of alpha 1 is equal to 1, f1 of alpha 2 equal to 0, f2 of alpha 1 equal to 0, and f2 of alpha 2 equal to 1. Now let xy be any element of R2. Then this from linear functions f1 of xy is nothing but some ax plus by, and f2 of xy is nothing but some cx plus by. And now if we find out the values of a, b, c, d, then we get two linearly independent elements f1 and f2, which are the elements of a basis set b star. B star. Now, as f1 of alpha 1 will be equal to 1, f1 of alpha 1 equal to 1, f1 of, and alpha 1 is 2 comma 1, which is equal to 1, which implies. Now from this f1 of xy is nothing but ax plus by. So put these values, we get f1. Put a equal to 2. Sorry. We plus b equal to 1, and f1 of alpha 2 equal to 0, which implies f1 of comma 1 equal to 0, 3a plus b equal to 0. So from this, now if we subtract these two, now we have to find out the values of a and b. Then we have to solve these two equations. 2a plus b equal to 1, 2a plus b equal to 1, and 3a plus b equal to 0. Now subtracting these two, we get minus a will be equal to 1, which implies a equal to minus 1. And by putting a equal to minus 1 in this equation, then we get minus of 2 plus b equal to 1, b equal to 1 plus 2, which is equal to 3. So b equal to 3. So here we get the values of a and b, a equal to minus 1 and b equal to 3. Now we have to find out the values of c and d. Now f2 of alpha 1, f2 of alpha 1 is equal to 0. Now f2 alpha 1 is 2 comma 1 equal to 0, which implies 2a plus b equal to 0, and f2 of alpha 2 is 3 comma 1, and which is equal to 1, which implies 3a plus b equal to 1. Now again we have to find out this two, 2a plus b equal to 0 and 3a plus b equal to 1. Now again subtracting these two, we get 2a minus 3a equal to minus of a will be equal to 0 minus 1 minus 1, which implies, sorry, cx plus dy, sorry, 2c plus b, 3c plus d. So we get 2c plus d equal to 0, 3c plus d equal to 1, and by subtracting minus equal to minus 1, which implies c is equal to 1, as c equal to 1, and by putting c equal to 1, we get d is equal to minus d. So we have to put this ABCD in these equations. We get f1 of xy is equal to a equal to minus 1, minus of x plus b is 3y, and f2 of xy is equal to c equal to 1 and b equal to minus of. So we say x plus 3, sorry, minus of x plus 3y comma x minus 2y is a dual basis. Thank you for watching the lecture.